Hello, everyone. So if you're just joining us here, welcome to this next talk at the Best Annual Institute. I'm Laura Wong, a program manager at Berkeley Lab, and I'd like to introduce our next speaker, Jared Langevin. Dr. Langevin is a research scientist at Lawrence Berkeley National Lab, where he models the national impacts of building efficiency on long-term energy use and CO2 emissions. He also develops decision support algorithms for energy flexible building operations and researches human and building interactions. Previously, he was a Science and Technology Policy Fellow at the US Department of Energy's Building Technologies Office, where he co-created the SCOUT program, an openly available model that enables rapid assessment of building energy and emissions reductions at regional and national scales. In this talk, Jared is going to introduce key methods and metrics for decarbonization modeling through the lens of SCOUT. And we'll try again to save some time at the end to address audience questions, which you can leave in the Q&A or chat functions. And with that, I'll hand it off to Jared.
Great, thanks so much, Laura. And yeah, wishing everybody a warm start to the new year. So thanks so much for the invitation to speak. Really appreciate it. If you followed the news lately, you've probably seen a lot of stories about the climate emergency and about goals to draw down carbon dioxide and other greenhouse gas emissions to zero or near zero in a few decades. And so what's often left unsaid in those stories is how policymakers determine that these kinds of emissions reductions goals are actually achievable. And so in the best cases, that kind of determination comes from mathematical models of low carbon futures, so computer simulations that are able to connect us between where we are now in terms of our energy use and emissions and where we actually need to get to by a certain point in the future. And today we're going to explore how some of those simulations work and the types of insights that they can provide. And the hope is that this kind of overview will help you interpret some of the other presentations in these sessions, as well as related materials on decarbonization that you might encounter in your day-to-day work. So let's begin with the backdrop for doing research and modeling on decarbonization. And Jessica has really set this up nicely already. So the Biden administration, as Jessica mentioned, has published a new set of goals for climate change mitigation in the long-term strategy document. And here again is that plot that Jessica showed, and it commits the US to a reduction of at least half of all emissions by 2030 and to net zero emissions by 2050. And these goals are consistent with the pathways laid out in a landmark 2018 report for keeping to less than a 1.5 degrees Celsius global temperature increase, which is a critical threshold that's been identified by climate scientists. So the US goal covers, as I think Jessica mentioned, emissions from all economic sectors. And the question of whether and how we can actually achieve such an ambition comes down to a more detailed understanding of emissions from specific economic sectors, which we gain through these mathematical models of those sectors, their emissions, and how those emissions might change over time under a certain set of conditions. So today we're going to focus on modeling for one of those sectors, buildings, and we're going to do so through the lens of a real publicly accessible modeling tool that Laura mentioned called SCOUT, and I developed that with other colleagues at the national labs. So keeping to that buildings context, we're going to cover 4 key topics, beginning with establishing the significance of the problem, and then moving through to examining elements of how this model works and the practical insights that these models can produce. And then we'll talk a little bit about future directions for this area of research. So why should we even care about buildings if we care about economy-wide decarbonization in the United States? Well, we can start with the fact that most US greenhouse gas emissions are carbon dioxide, or CO2. That's about 80%. And the strong majority of those CO2 emissions come from energy use. So it's about 92%, according to the EPA. And if you attribute current CO2 emissions down to economic sectors using the off-cited breakout that's shown in this chart, the contributions of what we would call buildings, residences and commercial businesses looks actually pretty small at 11%, which is less than a third of the largest sector, transportation. And keep an eye as well here on the strong contribution from the electricity sectors. That's 31%, which is near the top of the contributions, and a big part of the reason why this sector gets so much attention. So if we look at this in a more revealing way, using another chart from EIA, which breaks down the emissions by end use sector at right, buildings actually look a lot more important. So residential and commercial buildings here contribute 36% of US CO2 emissions across the end use sectors, and that's tied with transportation for the largest contribution. The difference between this story and that of the previous plot has to do with how the electric power sector, which you see here as a gray bar in the middle, is treated. So in fact, as this type of graphic nicely illustrates, 3/4 of electricity emissions come from electricity consumed in buildings. And in the previous chart, you could imagine taking a large bite out of that electricity piece of the pie, moving it over to a building emissions reduction opportunity, or at least framing it as a reduction opportunity that could come from developments in both the electricity and building sectors in parallel. So the larger point here is that when you talk about US emissions reductions, buildings are among the largest opportunities for interventions and should therefore be a primary focus of analysts and policymakers. And if we go deeper, there are many different energy end uses within the broader buildings tag that contribute to emissions and present opportunities for emissions reductions. So these two charts break out building energy use at left and emissions from that energy use at right by building type and energy end use services. And without getting too much into the terms here yet, I'd like to mainly like to focus on just how varied these results appear across different dimensions. So, first, the overall hierarchy of the bars is different depending on whether you look at energy on the left or emissions on the right. You also see different distribution of end uses, end use services, that's the colored segments here, or even entirely different end uses, depending on which building type you're examining, residential or commercial. And as you can imagine, each of these segments has its own dedicated set of solutions and researchers, which is what makes buildings really a very rich focus when it comes to decarbonization research. So we've established why buildings are important to decarbonization. And now the question is, how do we actually model building emissions reductions opportunities? So let's start here with model inputs. And here we're going to focus on two things, a reference case forecast that basically extrapolates historical trends into the future, and then a set or sets of interventions that could change those reference case trajectories. So the reference case forecast is characterized by first a segmentation of total energy use. So that's by region, building type, fuel type, end use, and technology. We also need a representation of building and technology stock evolution. So how many new homes are built, how many heating systems need replacements, et cetera. And then we track the characteristics of the typical installed technology unit for each of those energy use segments and of the mix of measures on the market that could replace the service of the typical unit. And that's important for kind of understanding the stocks and flows that I'll talk about in a minute. And lastly, we assume emissions intensities and energy prices, so CO2 and dollars per unit energy, and we couple those data with reference energy trends to get our emissions and cost results. So now regarding our interventions, for buildings, we classify these as efficiency, so that's persistent improvements in energy performance, flexibility, that's temporary modifications in energy load profiles to serve electricity grid needs, or fuel switching, which is also referred to as electrification, which, for example, would switch to serving home heating demands with clean electricity instead of natural gas fuel. And there are certain measures like efficient windows or controls that are unique in that they reduce the demand for energy services rather than reducing the energy needed to meet a given service level. Measures are typically defined in terms of a few key characteristics. So that includes the year where they enter the market, their cost, performance, and lifetime at the unit level. And for flexibility measures in particular, their ability to modify loads at the hourly time scale. And lastly, we also often need to keep an eye on what's going on with the energy supply. So these measures are all affecting energy demand. But on the supply side, particularly the carbon intensity of electricity is changing rapidly, and that can strongly affect the potential of electrification measures in particular. So for outputs, we have three main categories. There are energy outputs, that's energy consumption would be one of those, often described at the annual timescale in units like MMBTUs, quads, or terawatt hours. We can report site energy consumption, the consumption a consumer sees on their bill, or source energy consumption, and that's accounting for losses during electricity generation and distribution to consumers. For electricity in particular, we also have demand as a metric, and then that's the rate of electricity consumption, which is often averaged across an hour and is described in units like gigawatts or megawatts in these large scale models. So demand is an important metric for power grid operation and planning, and that determines how fast the electricity sector can decarbonize. And then there are emissions outputs. So often that's going to be an annual CO2 metric or CO2 equivalent metric in million metric tons. CO2 equivalent is a metric that it's a metric that essentially maps the effects of reducing non-CO2 greenhouse gases such as methane to the warming potential or GWP, as you'll hear it referred to, of CO2. The earlier graphic noted this distinction between direct and indirect emissions. So that refers to emissions from on-site combustion of fossil fuels, direct emissions, and then indirect emissions from upstream electricity generation. And then for those electricity emissions, there are two ways of calculating and reporting reductions. We can first assume the measures avoid emissions at the average intensity of the full generation stack, so to speak. So that may consist, for example, of some mix of coal, gas, and renewables. Or we can assume that the measures avoid emissions at the intensity of the next unit of electricity that would have been generated without the measure. So that would be referred to as the marginal emissions rate. And then the final metric is cost, and that's used to communicate how economically feasible a decarbonized future is. There are a couple of different components here that can be communicated: the cost of the technology that needs to be deployed, the energy costs that consumers will need to bear, or on the supply side, the cost to maintain and build out the electricity system to meet energy demands across future scenarios. So what are scenarios and how might they be constructed? Scenario analysis is really recognizing that there are a lot of different ways that key inputs to our models could develop into the future. And so that gives us so the scenario analysis gives us a way of communicating a range of potential outcomes under a range of plausible assumptions. Scenarios also allow us to explore sensitivities of outcomes to changes in assumptions that could represent, for example, the presence or absence of a certain type of policy program. In past work with the Scout modeling software, we've developed a set of core scenarios that we update annually. And this table shows you the key dimensions around which those are constructed. So the energy conservation measure, or ECM portfolio, how high performing are the technologies we make available to consumers on the market across the next few decades? What's going on in the electricity supply? So how aggressively does the grid decarbonize? And then end use electrification level. How much incentive do we provide consumers to switch from fossil-based services like heating and water heating to the same service served by electricity? So by manipulating those dimensions, we end up with 10 different scenarios, and I'll show you some results from their assessment in a subsequent slide. So we now have our key inputs, outputs, and scenario assumptions, and we need a way to link it all together. And so this diagram is what we use to describe the overall modeling approach for Scout. And you can see that the sets of inputs that I just described are shown in the left and right-hand green boxes here, respectively. I'd like to focus on the middle green box, which describes the analysis engine that we use to move from inputs to outputs in our simulations. So in this part of the model, we account for what I mentioned before, these stock and flow dynamics, and that's referring to the rates with which our building measures, or ECMs, are able to penetrate over time into their baseline markets. And you can think about this in terms of your own home. You know, at some point, your heating and cooling equipment wears out, needs to be replaced, or maybe you have a good reason to replace that equipment before it actually wears out. Or perhaps you live in a brand new home and that home needs to be served by new heating and cooling equipment. All of those cases are represented in our modeling. And along similar lines, when you do get to the point of needing new or replacement equipment, there are going to be multiple competing options on the market in most cases. And that competition between measures that could be adopted to provide the same service is the second thing that we need to represent in our modeling engine to get from our inputs to our outputs. We represent the trade-off consumers are likely to make here between how much a technology costs upfront and how much that technology costs to operate over its lifetime. And that's what gets us these technology market shares. So we can get into a little bit more detail on the staging of those calculations. So for a given measure in a given year, we start by asking how much energy or carbon or cost a measure could avoid if it fully penetrated its baseline energy use market overnight. And that's our technical potential. And it basically shows us the magnitude of our measure impacts in the absence of any assumption about stock turnover dynamics. To get to a real world outcome, we introduce the two considerations I mentioned on the last slide. So we account for these stock and flow dynamics, and the measure can't penetrate the entire stock of a comparable baseline technology. Only the portion of the stock that's newly added or up for replacement and retrofit in a given year, as I talked about. So that's one level of whittling down our impacts for that measure, as we show on the right-hand side of this plot. And then we account for ECM competition. So what other measures in our analysis provide the same service as the given measure? And can they provide that service in a way that's much more attractive cost-wise to consumers? And that's going to whittle down the potential impacts of a measure further, as you see again on the right. So depending on the audience, our analyses have pulled out results from each step in this staging, and any stage can really be illustrative. But if we're talking about realistic decarbonization scenarios and pathways for the building sector, we're mainly talking about results that are calculated after completing all of these steps. So before moving on to a few example applications from this type of modeling, I'd like to focus just on the special case of equipment electrification dynamics. Representing the rate at which buildings can electrify is really challenging. And unfortunately, right now, there aren't good models available for doing so at the level of individual consumer decision making. And that's an important gap, because representing that rate at which we electrify can be a crucial determinant of emissions reductions results, especially under an accelerated decarbonization of the electricity supply. And so in the absence of these kinds of bottom-up consumer models of electrification, we use external scenario analysis. And so as an example, this figure is showing several different scenarios of residential heating and water heating fuel switching rates over time. So that's the rate of electrification on the y-axis of each of these plots. And the year is shown on the x-axis going out to, I believe it's 2050. And these were developed by Guidehouse in support of a DOE heat pump initiative, using a combination of expert judgment and HVAC equipment sales and stock turnover analysis. So as you'll see, the rates are resolved by region and by vintage of equipment, so new or existing. In the context of a model like Scout, we can attach each of these switching trends to a specific segment of heating energy use. So for example, rates of conversion from natural gas furnaces to heat pumps in the Northeast in single family homes. And the nice thing about this approach is that it makes it easier to communicate electrification rates as part of model results. And in turn, it's easier for policymakers to map program goals to those rates. Great. Okay, so let's talk about some studies that turn these model capabilities into practical insights. One example is an analysis we did in 2019 to assess the plausibility of an 80% by 2050 emissions reduction goal set in an earlier version of the long-term strategy that was mentioned before. We used Scout to examine the question of, if we looked at an 80 by 2050 goal just within the context of the building sector, how feasible is it to get there? And as shown on the left, we found that we could very nearly get there. We got to about 78% with aggressive building efficiency and incentives for electrification alongside a higher end renewable energy forecast. The colored wedges, I'll note, are drawn from the set of scenarios that I introduced earlier, basically a subset of those scenarios. Most of the reductions that we see in that plot on the left are coming from changes in the electricity supply, since buildings intersect so strongly with the electricity supply. There is a complication here in that buildings can help enable that higher renewable penetration, which is something we didn't address with these results, but it has been of interest in our more recent work. And on the right, you can see that we're able to attribute high-level emissions reductions down to individual demand-side measures, these building measures, and assess whether those reductions are achieved cost-effectively. So for this one scenario that we pulled out here with higher fuel switching and higher renewable energy supply, we see strong cost-effective influence from heat pump water heaters, cold climate heat pumps, and then envelope and control technologies. The second study begins to address this question of how buildings can be a resource for the power grid as it moves towards decarbonization and high variable renewable energy supply. So here we use Scout coupled with Energy Plus models to assess the overall magnitude of the national building to grid resource in terms of both avoided electricity consumption and avoided hourly electricity demand. And we communicated how that resource is distributed across different regions, building types, and end uses out to the year 2050. So we found overall that the resource is quite large. It's enough to offset about a third of fossil-based electricity generation and half of all new fossil-based generation capacity that's added across the time horizon we looked at to 2050. We also found that much of the potential is concentrated in regions with high baseline electric loads and population. So that's the South and Southeast, the Great Lakes and Mid-Atlantic regions. And on a measures front, we found that measures for residential preconditioning using smart thermostats, installing heat pump water heaters, and management of commercial plug loads offer some of the greatest opportunities. So as in the previous study, this kind of modeling framework allows us to move between aggregated findings across the whole US and measure in context-specific results. The plots on the right really just demonstrate that there's a large amount of variation in the findings for this study, depending on which metric you look at, consumption or seasonal power demand. And depending on the region and building type of focus, there's also a lot of variation. So where regions here are shown on the x-axis of each plot, and the top and bottom rows here are showing residential and commercial building results respectively. The last study is one that's still in process that more directly focuses on describing the pathways towards emissions reductions in the building sector using a more aggressive set of assumptions than the previous studies that we've done. So here, essentially, we've updated the measure and scenario set we used in the first study I showed. And in particular, we added some of the grid interactive measures we developed for the second study I showed, and then bundled that into a picture of building emissions reduction potential under accelerated grid decarbonization that's consistent with the Biden plan of 100% decarbonization by 2035. So this is a waterfall chart, and it's one way of showing the progression towards 2050 and the sources of emissions reductions over time. So we move from the benchmark year of 2005 at the left, all the way through to 2030 in the middle, and then 2050 on the right. And what's shown here is total building sector emissions, energy-related emissions. So as we step down our emissions chart here, we can isolate the reductions that are specifically attributable to building measures in the analysis and look at them against those achieved through parallel decarbonization of the power grid. So our building measures can be further broken out here by type. I mentioned earlier, efficiency, flexibility, and fuel switching. And we can also break them out by building type and end use service, so that context that they apply to. Here, for example, we're seeing that reductions by 2030 come from a variety of end use services across building types, but that under the aggressively decarbonized grid, further reductions out to 2050 are attributable to fuel switching of heating and water heating. And then we can also look at what's left in 2050. So here, for example, we've still got about 10% of emissions remaining in 2050 for the building sector. And it's important to be realistic about what might remain and how it could be addressed, through further electrification, through renewable fuels, carbon offsetting as some examples. So this study is continuing to evolve. So stay tuned for publishable results in the next year, hopefully. And I'd like to close this presentation with just a look towards the future of building decarbonization modeling, beginning with a highlight of two emerging directions for the area. So first is an increasing ability to couple our models of how energy is used in buildings with power sector models. In the study I just mentioned, we're coupling Scout with a power sector model developed by Brattle called GridSim. And we're doing that to try to quantify the electricity system costs that could be avoided by adoption of building measures under rapid grid decarbonization. And the early results shown at left here are suggesting that these avoided costs are really substantial in the billions of dollars. The second new direction is toward a more complete assessment of sources of operational emissions in buildings, and in particular towards an assessment of fugitive emissions. So that's leaks of methane from natural gas supply to buildings, and then leaks of the refrigerants used in heat pumps and other building equipment. The limited existing work in this area that exists such as this unpublished study from UC Davis at Wright, which is comparing emissions from gas furnaces and heat pumps in homes. It suggests that methane leaks are particularly important. And of course, methane is even more of interest now, given recent US climate pledges in this area. And then lastly, as the field of decarbonization research grows, it's really important that we are able to develop a common basis for exchanging information and ideas about our models without too much friction. So here are two examples of attempts to facilitate that. At left, we've recently worked through the International Energy Agency research community to develop a classification scheme that allows us to quickly share and understand models that represent building energy use and emissions at scale. And along similar lines, this group's also developed a model reporting standard that should be published soon. On the right-hand side, we have a web platform that's managed by the International Institute of Applied Systems Analysis, and that was used to collect data for the IPCC's 1.5 degrees Celsius report that I alluded to earlier, and more recently for the 6th assessment report from the IPCC, which includes results on buildings. So researchers can contribute their data to this platform via a standard reporting template in Excel, and that includes a common set of variable definitions and model metadata fields, and that just makes it much easier to collect the kind of ensemble of results you see here on the right, even across a wide variety of modeling efforts. And in turn, that provides a much more robust understanding of where we can go with our emissions reductions pathways. So thanks very much for your attention, and glad to answer any questions in the time we have left.
Thank you, Jared. That really great talk, and thanks for breaking down the inputs and metrics that can be used in this powerful tool. I'm not seeing any questions or comments yet in chat. We do have a couple of minutes left, so if any of them come up, I'll read them out.
Laura, the questions are in the Q&A feature at the bottom.
Yeah, they were all from the previous.
Oh, I see.
Yeah, so I actually just called them answered because I didn't want to, they were. So Jared, I have a question for you. Can you talk about, we heard from Andrew McAllister this morning about California. And you do kind of the West as an entire region, right? So can you talk a little about the resolution of the different regions you look at, and how, for example, how the California situation might be different from the entire West that you model?
Yeah, so we've actually made a lot of improvement on that front, and that goes along with some of the improvement that our data sources from EIA have been making. So EIA uses 25 grid regions now to model the electricity supply, and so that I think in the past there was this big kind of WEC region, the West region that maybe you're referring to, that lumped together quite a diversity of grids of utilities together in one region. Right now, there's a lot more resolution out in the West, between Northern and Southern California, looking at the Pacific Northwest versus places like Nevada. And so we're capturing that in our modeling at this point, thanks to some of the resolution in the underlying data, which is important because if you look at especially the renewable forecast, they can be quite different, even between regions that are kind of adjacent in the Western part of the United States.
Thank you.
Thank you. There's a couple of questions that just came in. First one is, how do building operations affect the model?
Yeah, so I think what's assumed really here is kind of a typical set of building operations for each building type. So operations are generally characterized or classed by building type, and each building type, has a certain program, a certain use type that kind of dictates those operations. And in turn, those operations can be translated, operational schedules are translated into kind of a typical energy use pattern for that building, which is scaled up based on how much of that building there is in the overall stock, building stock for a region. So I think, particularly when we get into these flexibility measures, there's an important question about, variations from typical operations and how those might affect the potential for, energy flexibility. And for those specific modeling problems, we do try to explore those sensitivities a bit. But for the annual time scale, we're mostly using these kind of typical operational assumptions in our baseline forecast to get to the potential for these various measures.
And the time's right now 11:01. We're coming into a break, but I think we can use a little bit of extra time to answer this last question or a couple more questions, which is, to what extent do you incorporate non-energy benefits into effectiveness metrics?
Yeah, that's a great question. I mean, so I think that's, if I had to mention one other area, I guess, that is exciting for the future, I think that's definitely one of them. And in particular, looking at public health benefits, I think there's some good new data on attaching costs to public health outcomes or negative public health outcomes that could be avoided through energy efficiency and renewable energy projects. And EPA publishes those estimates. In the Scout tool that I mentioned, we actually do have a capability of attaching those public health cost adders onto some of the cost effectiveness assessments. But that's not something that we've actually done at a large scale in our studies yet that we've published. But there are some new data sets there that I think can help communicate those benefits.
Peter Crabtree sent a message asking, given the diversity of approaches towards emissions reduction that each state is taking, how does the model account for these differences?
Yeah, it's a great question. I mean, I think that so one of the ways that we try to handle that is we allow the capability to specify measures by region. So there may be some measures that apply in one region, whether that be a state or a utility region or something, or one of the other resolutions we use that does not apply in other regions. And so that's something that allows us a little bit of flexibility to try to capture the different ways that states are approaching the problem. There's also some of that captured kind of implicitly in the forecast we use of the electric grid. So our forecast of the electric grid are using kind of state level resolution in determining the emissions intensities for the grid. And so, that's another place where I think we're getting at some of that, regionally specific work that's being done.
Thank you so much, Jared.